This final assembly step transforms individual components into a complete functional agent by defining how everything connects and interacts. The code builds a state machine where LLM call handles reasoning and tool node executes calculations with clear transition rules between them. We'll see how the graph structure explicitly maps the agent's workflow, starting with LLM reasoning, conditionally routing to tool execution when needed, then looping back until a final answer is ready. The should continue function acts as the traffic controller, examining each LLM response to determine whether to call tools or end the process, while the compilation step optimizes this flow into an executable agent. You'll also notice how the visualization makes debugging intuitive by showing the actual execution paths. Hash build workflow. Agent builder equals Stategraph, messages state. Hash add nodes. Agent builder add node. LLM call. Agent builder add node. Tool node. Hash add edges to connect nodes. Agent builder add edge start. LLM call. Agent builder add conditional edges. LLM call. Should continue. Tool node end. Agent builder add edge tool node. LLM call. Hash compile the agent. Agent equals agent builder compile. Hash show the agent. From IPython, display import image display. Display image agent, get graph X-ray equals true. Draw mermaid PNG. Hash invoke. From LangChain, messages import human message. Messages equals human message. Content equals add 3 and 4. Messages equals agent invoke. Messages. For M in messages. M pretty print. This demonstrates the state machine pattern for building AI agents using Langgraph's Graph API, where workflows are modeled as directed graphs with explicit nodes for reasoning and tool execution. The key distinction from traditional agent code is how it separates the LLM's decision-making in LLM call from tool operations in tool node, with persistent state flowing between them via the messages state schema. This creates a cyclical reasoning loop that continues until the agent determines no further tool calls are needed. The pattern works by defining nodes as pure functions that transform state, connected by edges that implement control flow logic. The should continue conditional edge examines the LLM's output to route either back to tool execution or to termination, while the automatic cycle between tool node and LLM call handles the agent's core reasoning loop. This structure makes execution paths visible and modifiable, unlike linear agent code, where control flow is buried in conditional statements and loops. This approach matters because it solves 3 critical problems in agent development: observability, maintainability, and composability. The graph visualization, via Draw Mermaid PNG, provides immediate debugging insight into execution paths, while the node edge structure allows modifying workflows by adding or rearranging components rather than rewriting monolithic functions. The pattern particularly excels for production agents where you need to trace execution, handle complex workflows, or integrate multiple tools with clear separation between reasoning and action components. Let's break it down. Hash build workflow. Agent builder equals Stategraph, messages state. Initializes the agent's workflow using Langgraph's Stategraph, with messages state defining the data schema that flows between processing nodes. This establishes a state machine where each node performs a distinct operation, and edges determine execution flow based on conditions. The graph structure replaces linear agent code with explicit control paths between reasoning and tool use components. Agent builder, add node. LLM call. Agent builder, add node. Tool node. Registers 2 processing nodes in the state graph. LLM call for LLM reasoning, and tool node for tool execution. This separation creates a clean cycle where the LLM either terminates the workflow or delegates to tools, then receives the results for further reasoning. The should continue function, not shown here, will determine routing by returning either tool node for tool use or end to terminate. After tool execution, control always returns to LLM call, forming the agent's reasoning loop.
Agent equals agent builder compile.
This compiles the state graph into an executable agent workflow. The compilation step validates all node connections, optimizes execution paths, and prepares the graph for runtime, transforming the declarative definition into a runnable agent. Without compilation, the graph remains just a blueprint, not an operational system.
From IPython, display import image display.
Imports image and display from IPython's rich display system. This enables rendering the agent's state graph visualization directly in Jupyter notebooks, providing a mermaid JS diagram that shows the actual execution flow between LLM call and tool node for debugging and validation. The visualization requires GraphViz for full PNG rendering capability.
Display image agent, get graph X-ray equals true. Draw mermaid PNG.
Generates a visual representation of the agent's execution graph using mermaid syntax, rendered as a PNG. The X-ray equals true parameter reveals internal node connections for debugging, while draw mermaid PNG converts the graph structure into a displayable image. This visualization helps identify workflow bottlenecks and verify edge routing between the LLM and tool nodes.
From LangChain, messages import human message.
This builds a state machine agent using Langgraph Stategraph, where nodes represent processing steps and edges define transitions. The messages state schema defines what data flows between nodes, enabling type-safe message passing throughout the workflow. The graph starts at the LLM node, LLM call, then uses should continue to route either to the tool execution node, tool node, or terminate. The cyclical edge from tool node back to LLM call creates the agent's reasoning loop, continuing until termination conditions are met. Compilation validates connections and optimizes execution paths, while draw mermaid PNG generates a visual representation that helps debug complex workflows. The final invocation demonstrates the complete cycle. Human input right arrow, LLM reasoning right arrow tool execution, right arrow response generation.
Messages equals human message. Content equals add 3 and 4.
This initializes the agent's workflow using Langgraph state machine pattern. The state graph with messages state defines both the data schema flowing between nodes and the execution framework, where each node represents a distinct processing step. The human message creates the initial input payload with content, add 3 and 4, formatted for LangChain's message handling system. This establishes the concrete user request that will enter the workflow at the LLM call node, demonstrating how real user input integrates with the graph structure. The list wrapper enables handling multiple messages in the state, though this example uses a single message.
Messages equals agent invoke. Messages.
Executes the agent with the prepared message history wrapped in the required input schema. The invoke method triggers the state graph's execution flow starting at LLM call, with the agent managing all subsequent node transitions and termination conditions. This follows Langgraph's standard pattern, where agents process messages through defined nodes until reaching end or satisfying termination criteria.
For M in messages. M pretty print.
This implements the agent's execution loop, by iterating through response messages and displaying them. The pretty print method formats complex message objects, including tool outputs, AI responses, and metadata, into readable text, replacing raw object dumps with structured output. This final step reveals the complete interaction history after the graph-based agent processes the initial, add 3 and 4, request through its reasoning execution cycle. Langgraph state machine pattern. This code implements a cyclical agent workflow where the Stategraph orchestrates message passing between an LLM reasoning node, LLM call, and a tool execution node, tool node, with conditional routing determining whether to continue processing or terminate. The should continue function acts as the decision point between LLM tool iterations, though its exact routing logic isn't shown in this snippet. It must return either tool node for continued processing or end for termination. Visualizing with Draw Mermaid PNG converts the execution graph into a debuggable diagram, requiring GraphViz for full functionality, while the messages state schema explicitly defines what message data flows between nodes at each transition. The compilation step both validates node connections and optimizes the execution path before invocation.
The graph that draws itself erases all paths